Today in AC electrical circuits, we're going to take a look at lab number 9, AC Thevenin's and Norton's theorems. Under the objective, Thevenin's and Norton's theorems will be examined for the AC case. The Thevenin source voltage, Norton current, and Thevenin-Norton impedance will be determined experimentally and compared to theory. Loads will be examined when driven by both an arbitrary circuit and that circuit's Thevenin equivalent to determine if the resulting load potentials are indeed identical. Under reference sections, I'm referring to Sham's Outlines, Basic Electricity, 2nd edition. We need to review Chapter 9 on Network Calculations, Thevenin and Norton's Theorems. Chapter 18, AC Circuit Analysis with Complex Numbers. And a review of Chapter 14 talks about capacitance and capacitive reactance. So hopefully from your DC circuit analysis you remember that Thevenin's theorem is a method used to change a complex circuit into a simple equivalent circuit. So as a refresher, looking at figure 9.9, we can see we have an example of Thevenin's equivalent with a load. So we took a complex circuit and we converted it into Thevenin's equivalent voltage and equivalent resistance with our load on it. And you might want to review Norton's theorem. And you might want to review figure 9-12, equivalent circuits. So for Thevenin's equivalent, we have Thevenin's voltage and Thevenin's resistance. And for Norton's equivalent circuit, we have a current source in parallel with Norton's resistance. And you'll notice that Norton's resistance is identical to Thevenin's resistance. And we'll be using that today in the lab. Hopefully, Chapter 18 is still fresh in your mind because we will be using AC circuit analysis with Norton and Thevenin today. And make sure that you have reviewed Chapter 14 on capacitance and capacitive reactance. And you may want to review the effect of R and XC in series, where VC makes an angle of -90 degrees to VR and I, which is the reference. So theory overview states that Thevenin's theorem states that any linear two-terminal AC network can be replaced by a single voltage source with series impedance. For Norton's theorem, it is replaced by a single current source in parallel with an impedance. So just like a DC circuit, except now we're working with AC voltages and of course impedances instead of resistances. So just like when we did the DC circuit analysis for Thevenin, we're going to measure Thevenin's voltage and Thevenin's impedance. However, you'll notice in the overview it says if an impedance meter is available, an easy method of doing this in the lab is to replace the sources with appropriate impedance values and apply the impedance meter to the output terminals of the circuit. Unfortunately, we do not have an impedance meter, so what we're going to be doing is we're going to find Z Thevenin by the formula Z Thevenin equals E Thevenin divided by I Norton. Now that's just straight Ohm's law, except in this case, Z is an impedance, and that implies that either E Thevenin or I Norton will have a phase angle associated with it. So under equipment, we're going to use an AC function generator. In our case, it's the circuit test SWF 7000. I'm not going to bother with its serial number. The oscilloscope is the Tektronix, and I'm using the TDS 1002. Don't bother with its serial number. And the digital multimeter will be the Mastech MSM 9803, and I'm not going to bother with its serial number. Under components, I've left a place here for you to do the actual measurements so you know you have the right part and how out of tolerance it might be. Capacitances are always a fair distance out of tolerance. So you can see my 0.47 microfarad is actually 0.455 microfarads. My 10 ohm resistor is actually 10.8 ohms. My 1K ohm resistor is 978 ohms. My 1.5K ohm resistor is 1.484K. And my 2.2K ohm resistor is 2.177K ohms. So under procedure, step number 1, it says for the circuit of figure 9.1, calculate the voltage across the 1K ohm load and phase angle using R1 equal to 1.5K, R2 is equal to 2.2K, and C is equal to 0.47 microfarads. It has a 2 volt peak to peak 1 kilohertz source. We're to record this value in table 9.1. Note it will be easier to do these calculations using Thevenin's equivalent circuit. We're also to calculate the expected Thevenin voltage, Norton current, and Thevenin Norton impedance with phase angles. We're to record these values in table 9.2. A calculation page has been provided for you. So you can see under lab schematic we have two figures. One is 9.1, which is our original circuit. Figure 9.2 is Thevenin's equivalent circuit. So I've gone ahead and labeled my known components. So R1 is 1.5K, R2 is 2.2K, C is 0.47 microfarads, our load resistance is going to be 1K, and our source is 2 volts peak to peak at 1 kilohertz. Remember, to Thevenize the circuit, we remove the load, replace the source with its ideal internal resistance, which is 0 ohms. So looking back into the circuit, we're going to see our capacitor, and that's going to be XC because it's an AC circuit. And then we're going to see R1 in parallel with R2. So I think the first step will be to calculate R1 in parallel with R2. Then we'll add XC, which will give us a phase angle. And that will give us our Thevenin's impedance looking back into the circuit. To find Thevenin's voltage, all we've got really is a voltage divider circuit, because once we remove the load there is no current flowing through the capacitor. So it simply becomes 2.2K over 1.5K plus 2.2K times the applied voltage. So I've given you a page to do your calculations on. The first section is labeled Thevenin. And what we've got here is our load is 1K, C is 0.47 microfarads, R1 is 1.5K, R2 is 2.2K, and our Vin is 2 volts peak to peak at a frequency at 1 kilohertz. So the first part is to find out what R1 is in parallel with R2. So the formula I'm going to use is the products over the sum. So I take 1.5K times 2.2K over 1.5K plus 2.2K, and that equals 891.892 ohms. Now remember, we're going to need a phase angle, and when you have resistors in a circuit, they do not generate a phase angle, so the phase angle will be 0 degrees. Next, I need to know what XC is, and I've given you the formula, 1 over 2 pi FC, and remember there's a minus sign in front of it, which means it acts at minus 90 degrees. So that becomes 1 over 2 pi. Frequency is 1 kilohertz, capacitance is 0.47 microfarads. So that works out to 338.628 ohms at an angle of minus 90 degrees. Now to find Z Thevenin, we're going to add R parallel to XC. Now I want to show you how to set up your calculator to do that right now. So to set up my calculator, the first thing I'm going to do is click on Setup. And I want to go to FSE, so that's 1. And I want engineering notation, so that's 2. I want to go back to Setup, and I want to change the number of decimal places, so I'm going to select 2 for tab, and I like 3 decimal places. Next, I'm going to go to Mode, and I'm going to use the down arrow key and select 3 for complex. You'll notice in the top left-hand corner it says XY. So now I press the second function and I press the 8 key, and that puts it in polar form. You notice a little R theta in the top left-hand corner. So this is my calculator set up to use today. So to calculate Z Thevenin, it's equal to R parallel plus XC. So that's equal to 891.892 ohms. Remember, that's at an angle of 0 degrees. Plus XC, which is 338.628 ohms at an angle of minus 90 degrees. That's going to be equal to 954.013 at an angle of minus 20.79 degrees. So to type that in my calculator, I press 891.892. Now my angle key is below my DMS key. This is at 0 degrees, so when I press the angle key, it asks me for an angle, and I'm just going to type in 0. To that I need to add XC, so I press plus, and XC is 338.628. Now that's at an angle, so I press the angle key, and it's at an angle of 90, and it's minus 90, so I press the plus minus button, and it puts a minus in front of it. Then I press the equal key, and it tells me it's 954.013. Now to get the angle, I press the second function, and then I press the EXP key, and it tells me I have an angle of minus 20.79 degrees. Now to calculate E Thevenin, all I'm going to do is use a voltage divider. So that's R2 over R1 plus R2 times my applied voltage Vin. So that's 2.2K divided by 1.5K plus 2.2K times 2 volts peak to peak, and all of these were at an angle of 0 degrees, so you can leave that off. and that equals 1.189 volts peak to peak at an angle of 0 degrees. Now to calculate Norton's current, it's basic Ohm's law, so it's going to be E Thevenin divided by Z Thevenin. So that becomes 1.189 volts peak to peak at 0 degrees that we calculated above, divided by 954.013 at an angle of minus 20.79 degrees, which was also calculated above. And that will work out to 1.246 milliamps at an angle of plus 20.79 degrees. To calculate V load, all we do is use voltage divider. So we're going to take RL over RL plus Z Thevenin times E Thevenin. So calculating V load using the Thevenized circuit is a lot easier than trying to figure out on the original circuit. So the formula becomes 1K, and remember it's at an angle of 0 degrees, divided by 1K at an angle of 0 degrees, plus 954.013 at an angle of minus 20.79 degrees. We multiply this by Thevenin's voltage of 1.189 volts peak to peak at an angle of 0 degrees. And this will work out to 618.639 millivolts peak to peak at an angle of plus 10.148 degrees. So on table 9.1, for V-load theory, I've recorded the voltage as 618.639 millivolts peak to peak, and the phase angle is 10.148 degrees. So under table 9.2, for E Thevenin theory, magnitude is 1.189 volts peak to peak, and the phase is 0 degrees. For I Norton, the magnitude is 1.246 milliamps peak to peak, and the phase is 20.79 degrees. For Z Thevenin, the magnitude is 954.013, and the phase is minus 20.79 degrees. Under procedure, step number 2, we're to build the circuit of figure 9.1. We're to set the function generator to a 1 kilohertz sine wave at 2 volts peak to peak. So this must be set up on the oscilloscope in order to see the 2 volts peak to peak. We're to make sure that the bandwidth limit of the oscilloscope is engaged. This will reduce the signal noise and make for more accurate readings. We're to measure the load voltage and phase angle and record it in table 9.1 as V load original. So when wiring up my circuit, referring to figure 9.1, I'm going to try and follow the layout set out here and duplicate that on my trainer. So looking at the circuit on my trainer, my input voltage from the function generator, remember this is 2 volts peak to peak at 1 kilohertz, so that comes from the function generator. It comes into R1, which is 1.5K. It joins up in this bus with R2, which is 2.2K, and goes back to the common of the function generator. At that same point, it makes contact with the 0.47 microfarad capacitor. Now my 0.47 microfarad capacitor is labeled 474, so that would be 470,000 picofarads, or 470 nanofarads, or 0.47 microfarads. Now that's going to join in this bus with our load, which is 1K ohms, and it comes back, and I have to have a little black jumper wire to continue the bus line over to the common that goes back to the common of the function generator. This yellow line is going to go to channel 2 of my oscilloscope because that's V load, or the output voltage. Channel 1 of my oscilloscope will join with the function generator, and that will be my input voltage of 2 volts peak to peak at 1 kilohertz. So the first thing you need to do is set up your input voltage. So I wanted to show you the display on my oscilloscope. You notice channel 1 frequency is at about 1 kilohertz, and channel 1 peak to peak voltage is approximately 2 volts peak to peak. Remember, channel 1 needs to be set up for AC coupling. We should put the bandwidth limit on. Volts per division should be coarse, and I'm using a ×1 probe. Make sure that invert is off. When you press the measure button, make sure you set up channel 1 for frequency and channel 1 for peak to peak voltage. And then for your third item, make sure you set it to channel 2, and you want it to be peak to peak voltage as well. Now looking at channel 2, if you press the channel 2 menu button, you can see the coupling is AC, the bandwidth limit is on, volts per division is coarse, our probe is 1 times, and the invert is off. So pressing the measure button, you can see our channel 2 peak to peak voltage is 640 millivolts. Now we need to measure the phase angle between the two waveforms. So I've shown you how to do this in previous labs. I'm going to change the volts per division for channel 1 and channel 2 to get my lines going as vertical as possible. I'm going to put on the cursors, and I want them to be type time. My source is channel 1. So I position one cursor at the zero crossing of one waveform, the second cursor at the second crossing of the second waveform. Very important to make sure that the zero lines are both on 0 for both channel 1 and channel 2. And the delta is 30 microseconds. Now referring back to our original waveforms, the larger waveform being our input voltage, the smaller waveform being our output voltage, you can see that it is indeed leading. So when it's leading, it's a positive phase angle. So on table 9.1, for V load original, I've recorded the voltage as 640 millivolts peak to peak. The phase angle was plus 30 microseconds. So we have to remember the formula. The period is equal to 1 over the frequency, so that's equal to 1 millisecond. And the phase angle is equal to the change in time, or delta t, over the period times 360. So if you take 30 microseconds and divide it by 1 millisecond, multiply it by 360, you come up with 10.8 degrees. Under procedure, step number 3, we're to remove the load. That's the 1K ohm load resistor. We're to measure the unloaded output voltage and phase angle. This is the experimental Thevenin voltage. We're to record it in table 9.2. So under procedure, step number 3, I'm to remove the load resistance. So all I'm going to do is pull out the 1K ohm resistor. So looking at the oscilloscope, you can see channel 2 is reading 1.2 volts peak to peak, and the waveform looks like it's in phase, so that's 0 degrees. So on table 9.2 for E Thevenin, the experimental magnitude is recorded as 1.20 volts peak to peak, and the experimental phase angle is 0 degrees. Under procedure, step number 4, we're to replace the load with a 10 ohm sensing resistor. We're to measure the output voltage and phase angle. It says this is the experimental Norton short circuit current when you divide the voltage by the 10 ohm sensing resistor. Remember Ohm's law, and that I equals V over R, and R is equal to 10 ohms. It says dividing the Thevenin voltage by the Norton current gives you the Thevenin-Norton impedance Z Thevenin. This is the experimental Thevenin impedance. Record these values in table 9.2 and compare with the theoretical values. I've now replaced my load resistor with a 10 ohm resistor to create a short in my circuit so I can measure I Norton. So all I'm going to do is take the voltage drop across the 10 ohm resistor, divide it by the 10 ohms, and that will give me I Norton. So looking at my output, you can see I'm getting about 13.4 millivolts, and notice I've had to adjust my volts per division all the way down to 5 millivolts. It's a very small signal. So putting on my cursors to type time, you can see that I've had to readjust my volts per division for both channels to get the lines as vertical so I can find the zero crossing point. I've also gone to the acquire menu and changed it to averages, and so I'm using 64 averages to get that line as smooth as possible to find the exact zero crossing. And you can see that it is actually leading, so it's positive 62 microseconds. In table 9.2, for I Norton experimental, the magnitude was 13.4 millivolts. Remember to divide it by the 10 ohm sensing resistor, and that works out to 1.34 milliamps. For the phase angle, delta T was 62 microseconds, and when you divide that by 1 millisecond times 360, that works out to 22.3 degrees. Z Thevenin, experimental, needs to be calculated, and we calculate it by using Z Thevenin equals E Thevenin over I Norton. So this is 1.2 volts at 0 degrees divided by 1.34 milliamps at an angle of 22.3 degrees, and that works out to 895.5 ohms, and it's at an angle of minus 22.3 degrees. The percent deviation for both voltage and phase angle I'm going to leave you to calculate. Under procedure, step number 5, it says to build the Thevenin equivalent circuit of figure 9.2, you need to create Z Thevenin. To make this lab as simple as possible, we will assume C Thevenin will stay as originally specified as 0.47 microfarads. Then you only need to calculate R Thevenin, having already calculated Z Thevenin and knowing C Thevenin. You will find space to do this calculation on the provided calculation page. So to calculate R Thevenin, we're going to leave C Thevenin as 0.47 microfarads, So R Thevenin is equal to Z Thevenin minus XC. So that's going to be 954.013 at an angle of minus 20.79 degrees, minus XC, which is 338.628 at an angle of minus 90 degrees. So that works out to 891.895 at an angle of 0 degrees. Now I want to show you this on the calculator. So on my calculator, what I'm going to do is press Setup, press 1 for FSE, and I want it to be fixed. So I'm going to press 0 for fixed. Okay, so I'm going to type in my 954.013, and it's going to be at an angle of 20.79, and press the plus minus button. And from that I want to subtract XC, so I press minus 338.628, and it's going to be at an angle of 90 degrees minus. So that equals 891.895. And when I press second function, EXP, it gives me an angle of 0 degrees. Now if I go back to Setup and change my FSE to engineering notation, you'll notice my angle is 449.77 microdegrees. It's times 10 to the power of minus 6. And this is close enough to 0, so that's why I pressed Setup, FSE, 0 for fixed, and you can see it rounds it up to 0 degrees for you. Under Procedures, step number 6, it says using the Thevenin resistance and capacitance, build the Thevenin equivalent circuit of figure 9.2. And we're to apply the 1K ohm load resistor. We're to measure the load voltage and phase angle and record it in table 9.1. We're to compare the values of the original non-Thevenized circuit and determine the deviation between the original and Thevenized circuits. So referring back to figure 9.2, my E Thevenin is going to be 1.189 volts peak to peak. The angle is 0 degrees and it's at 1 kilohertz. My load resistor is the 1K, so I've drawn that in. My C Thevenin is still the 0.47 microfarad capacitor, so it's still labeled 474. R Thevenin is 892 ohms, and I'm going to use a 5K ohm potentiometer, so that's going to be labeled 502. One leg goes to my power supply, the center leg goes to the capacitor, and the third leg is not used. So I just want to give you a good close-up of my circuit. You can see the red line I'm going to connect to my ohm meter. The black line goes to the common of my ohm meter. So I can measure the resistance across the two leads. One lead going in the top hole, one lead from the center goes in the next hole, and the bottom of the potentiometer, the last lead, goes in the third hole, and you'll notice nothing is connected to it. The capacitor is connected to the center pin, which right now has the black lead going to the common of the ohm meter. The capacitor is connected to my load resistor, and the output sensing wire that goes to channel 2 of the oscilloscope. The bottom of my 1K ohm load resistor goes to this black wire that will go back to the common of the function generator, but for right now all I'm going to do is measure the resistance and adjust my potentiometer. So I've adjusted my potentiometer to get exactly 892 ohms. So I've now taken the black wire out of the center of the potentiometer and moved it down, so it's now going to be the common of my function generator. So I just wanted to show you on my circuit the common of the function generator and the output of the function generator, the common of channel 1 and channel 2, so all the black leads go together and they join at the bottom of my 1K ohm load resistor. The output of my function generator and channel 1 of the oscilloscope go to the top pin of my potentiometer. The center pin of my potentiometer goes to my capacitor. My capacitor goes to the top of the 1K ohm load resistor, and channel 2 of the oscilloscope is looking at the voltage at the top of the load resistor with respect to the common at the bottom of the resistor. And you'll notice I've removed the ohm meter from my circuit because you cannot measure resistance in a powered circuit. So looking at the output of my oscilloscope, you can see the frequency is close to 1 kilohertz. It's 1.01 kilohertz. My channel 1 peak to peak, we were trying to get 1.189 volts peak to peak. I've got 1.19. And my channel 2 output is 612 millivolts. So looking at the output on my oscilloscope, you can see I've changed the volts per division for both channels to get the lines running as vertical as possible. And I've changed the seconds per division to get as much space between them as possible. I've now got the cursors set to type time. The source is channel 1, and my delta between the two waveforms is 29.6 microseconds. And because my output waveform is on the left-hand side of my input waveform, it's plus 29.6 microseconds. So on table 9.1 for V-load Thevenin, I've recorded the voltage as 612 millivolts peak to peak. The phase angle was plus 29.6 microseconds, and when you divide it by the 1 millisecond period and multiply it by 360 degrees, rounding up you get 10.7 degrees. Now under procedure, step 6, we're to determine the deviation. I'll let you do the calculation, but keep in mind it's the deviation between the original and Thevenized circuits. On the last page of the lab, there are 3 questions for you to answer based on your calculations, observations, and conclusions of this lab. When you've completed the lab, leave your circuit set up on your trainer so your instructor can verify its operation, and then they will initial your lab to indicate that it is complete.